Have a seat. So, a very special form of the energy equation, single inlet, single exit, steady, incompressible, isothermal, and a very drastic approximation called loss free. Flow is taken to be loss free, that is free of viscous dissipation, and that is equivalent to setting viscosity equal to 0. So, such a flow as opposed to real flow is called ideal. So, under these conditions the energy equation reduces to what is called Bernoulli's equation. So, which instead of writing E2 minus E1 less than 0, it becomes E2 minus E1 equal to 0. You can think of it as a limiting case. And writing E, where E is P over rho plus U square over 2 plus G z. So, by and large Bernoulli equation has no application except in a few cases, in fact very few, but some people use Bernoulli equation as a starting point and then bring in real life effects. This is one line of thinking, but otherwise you have to use the full form of first and second laws of thermodynamics. One application given in the book is pitot tube, and a variant of pitot tube called pitot static tube. Whose construction, and as the name suggests, it is just a tube, but it is a bent tube, a tube with a right angle bend. So, this is point 1 and the nose of this tube is point 2. So, it is just a tube which is placed in the flow. You can think of the tube to be a, well, though it is called a tube, you can think of it as a rod which has been bent and it is placed in the flow. Now, you have studied u dot n equal to 0 for the solid surface many times. So, on the nose of this tube, which is shown as point 2, this is a very small diameter tube. Okay. Imagine a small diameter tube placed in a flow field. The flow field is infinite in expanse, it's flow taking place everywhere, and you insert a right angle tube. This tube, for a start, you can think of it as a rod, solid rod, and the mouth, not the mouth, the nose, the nose of which will block the flow and bring velocity to 0. So, if you think of a control volume that contains 1 and 2, some flow has to go from the sides, because the flow is blocked on the other side. But if you are along the axis, that means you shrink the control volume, you just shrink it. So, you have a stream tube of very small diameter. So, along the axis of this pitot tube. So, this is called a pitot tube. If you consider a small diameter control volume containing points 1 and 2, the solid surface is only a 2, but so between 1 and 2 there are no solid surfaces, and you may expect the flow to be loss free. That means Bernoulli's equation can be applied between 1 and 2, but at point 2 velocity is 0. So, it has to be accompanied by an increase in pressure, and there is no change in the elevation between points 1 and 2. So, you get P 1 over rho plus u 1 square over 2 equal to P 2 over rho, which tells you that u 1 is equal to 2 times P 2 minus P 1 over rho. Okay, now this solid rod has brought the fluid particles to rest. Now, if you can measure P 2 somehow relative to P 1. So, for that you can think of a very small diameter hole which serves as a tap. A tap is a very small hole through which fluid pressure is communicated. Do you remember how pressure difference is measured? We had studied manometry long ago. So, a manometer is a gadget that helps you measure pressure difference. So, P 2 minus P 1 can be measured using a, let us say, a U tube manometer. Okay. So, for which you have to connect these points 1 and 2. So, this pitot tube usually will have a very narrow hole, small diameter hole through which pressure P 2. So, this hole does not affect the pressure at point 2, hopefully. So, I will show a U tube here which measures P 2 minus P 1. P 2 is greater than P 1. So, the liquid level so this is point 2, this is point 1. So, this difference in levels of the manometric liquid will help you measure P 2 minus P 1. So, this pitot tube is a very commonly used device for measurement of velocity. Okay. So, we looked at measurement of force using velocity. If you remember the wake deficit method, there was a velocity deficit in the wake using which we found the force acting on the object. Now, how do you measure velocity? One possibility is to use a pitot tube. So, this tube is placed, you have to move it in the wake and measure the velocity distribution. Okay. So, this gadget becomes a useful approach to measuring velocity. Now, to measure velocity, so we use the pitot tube. A pitot static tube is a composite device that helps you measure P1, P2 jointly. So, if you want to measure P1, you remember our discussions on measurement of pressure. Let us say this is a duct, then the pressure is the component of stress that acts normal to the surface. So, you create a small tap and let that pressure act on another surface, that could be a diaphragm or a spring or a liquid column in a manometer. So, you can measure P1 by having a hole on the side of the tube. So, this is the wall of the tube. So, this will give you P1 and the main axis will give you P2. So, the same sensor can be used to measure P1, P2, but it will be a bulkier device. But if you have knowledge of P1 somehow, then it is enough to measure P2. So, then the probe can become smaller. But the point is, you can use Bernoulli equation and connect velocity to change in pressure. Okay. So, such applications are very few. Much of the time you have to use the full form of the energy equation. So, now let us proceed to evaluation of the energy equation. That means, we had an expression like this, E2 minus E1 less than 0. This is when shaft work is 0. So, remember that we are using lowercase w for shaft work per unit mass flow rate, small q for heat transfer per unit mass flow rate, and capital Q is small q times m dot, capital W is small w times m dot. So, this is a special form of the energy equation. So, it is not adequate, I think we discussed previously. Less than 0 will gives you some limiting results, but how much is it? Okay. So, just going back a step, we had written this equal to Q, okay, which is less than 0 from second law. Now, this Q is just by convention, it is written as minus G H loss. Okay, what are the units of Q? That would be meter per second whole square, right? It is like u square over 2. So, it is expressed as y minus, because Q is less than 0. So, G times H, which will give you the correct units. So, H is then said to be the head loss. This H has units of meters. So, it is called a head loss, and sometimes now why does this loss take place? Because of viscous dissipation. Okay. So, because of viscosity, which is connected to friction. So, the other symbol, both symbols are used in the book. The other symbol used is HF. So, let us say somehow I give you the value of HF. HF will be in meters. So, that is a positive quantity, because you have already accounted for the sign. So, I may tell you HF in this problem is 5 meters. So, the moment you know HF, you can now evaluate this equation. Okay. So, let us say flow through a tube 1 2, there is no change in velocity, there is no change in elevation. So, there is only a change in pressure. So, you have P 2 minus P 1 over rho is equal to minus G H F or H loss. So, this is now it is not an inequality, it is now an equation. Okay. So, if data is available to you on head loss, in some new application you can find the pressure drop. Let us look at this problem. This flow is from 1 to 2 and this is a pump. So, you will have E 2 minus E 1 equal to minus G H F minus W s. This W is lowercase w. Okay. So, a pump takes in work. So, as per our, if you convert W s in terms of pump work, it will become minus W p, and W p is a positive quantity. Okay. So, but when you write shaft work, you write it as Q minus W s, that is second law. I mean that is the first law. With the sign convention, it becomes, that means Q is less than 0, it becomes the second law. So, now we have an equation. Now, there is pump is a small device. So, no change in elevation, no change in velocity. Why? Because let us say the tubes are of equal diameter, it is a steady flow process, this flow going through the pump, no change in velocity, no change in elevation, because pump is a small gadget. So, it is only a change in pressure. Now, I am just defining the problem further. Let us say the pump takes water from a low level water reservoir. And pumps water. So, this is a low level water reservoir and pumps it back into the atmosphere. Okay. So, practically it starts from atmospheric pressure and it is dumping water into atmospheric pressure. So, what is it that the pump has to do? Only overcome losses in the tube, assuming of course, the pump will also have losses. For the time being, we are working with an ideal pump, no losses in the pump. So, all the losses are localized in the tube. So, let us say localized is the word. So, P 1 equal to P 2, Z 1 equal to Z 2, U 1 equal to U 2. Okay. So, that means E 2 minus E 1 is 0 and you get W s equal to minus G H f, and the pump work is m dot G H f. So, when you express in terms of pump work, you do not say it is minus so many units. When you say WP, you say it is 10 kilowatts or 1 kilowatt or 10 watts. Okay. But if it is shaft work, you have to put a sign. So, small Ws is minus GHF, indicating that the pump will require work to be supplied to the fluid in the controlled volume, which will overcome losses taking place in the tube. Of course, there could be some losses in the inlet tube also. I am intuitively assuming that the inlet tube is short. Why? We will see that. Usually, the inlet tube of a pump is short, delivery tube is long. So, we will study the reasons for it as we go along. So, assuming that inlet tube is of short length and losses are not very much. You remember that losses will be proportional to length. So, it may seem rather trivial that if HF is given, yes, I can solve the problem. Okay, so, the inequality has become an equality. So, here is an example where pump work overcomes the losses in the tube. Let us look at another example where this is 1, this is 2 and this is a pump. Where the pump takes water from a, let us say, a small pond of very low elevation and delivers it to the roof of your hostel. Okay. So, now the tube is vertical. Now, here is a caution, do not mix up head difference with the length of the tube. Should the two be equal? Not necessarily, because your tube can go all over the place and then reach the top. So, length can be any, do not assume that length and elevation difference are equal. Okay. Now, let me make this problem a little more elaborate. So, this is the roof and it is delivered into a tank. So, this water coming out, this is 0.2. So, P2 is atmospheric. And let us say this is the water level in the reservoir. Okay, so, you have the choice of picking your inlet as 0.1 here, or it can be inlet to the pump, it can be inlet to the tube on the suction side of the pump. So, 0.1 can be placed anywhere you want. So, what is the advantage of putting it at 1? You remember that in a reservoir, the level is not changing with time. So, velocities are 0. Okay. You know the elevation, you know pressure. What is pressure at the free surface? Atmospheric. So, it is an advantage in keeping 0.1 over there. So, now let us write the energy equation with losses specified as minus GH, minus GHF. So, E2 minus E1 is equal to minus GHF minus Ws. This is energy equation, where losses, I mean wherever they are possible, should be accounted for. So, certainly there are losses in the tube part of the hydraulic system. What about losses in the reservoir? The velocities there are negligible. So, the losses taking place inside the reservoir are very small. I mean, our reference point is Newton's parallel plate experiment. If velocity is small, you won't have losses. You remember wall shear stress and quantities like that, they are all related to velocity, and velocity is small, losses are small. So, losses in the reservoir are 0. There could be some losses in the pump, but we are treating the pump to be ideal for the time being. So, all the losses will take place in the tubing. So, this E 2 minus E 1, change in pressure 0, kinetic energy U 2 square over 2 plus if you measure elevation from point 1, so it is plus G h. H is the difference in elevation between points 1 and 2. Minus atmospheric pressure cancels off, gravitational potential cancels off, velocity is 0. So, this is equal to minus G h f minus W s. So, W s is equal to minus G h f minus G capital H minus U 2 square over 2, and you write pump work is equal to m dot G h f plus G h plus U 2 square over 2. Okay. So, if loss is specified, you can actually carry out numerical calculations. You can also see that the pump will then have to pay for what? The losses, for delivering kinetic energy to the fluid, and for raising it through a distance capital H. Okay. So, you can think of it as internal dissipation, gravitational head and kinetic. This is what the pump is accounting for. So, in these calculations H f has to be given. So, again going back to the book, you have a whole lot of questions where H f is given, treating losses to be 5 meter per second, not 5 meters. Find the pump power. So, you can carry out these calculations. But in general H f, the losses will depend on certainly the properties, length of the tube, diameter of the tube and velocity. Right? We said velocity is 0, losses are 0. So, it is a function of many quantities. It depends on whether you are working with water or sea water or air or oil. Now, here I have assumed that the geometry is a tube of length L and diameter d. So, this is for a tube. In case of a pump, losses may depend on the casing. Pump will have a casing diameter. It will depend on RPM. It will depend on the blade geometry. So, losses are geometry specific and device specific. So, how can we specify losses? Now, should not come as a big surprise to you if you have done problems related to, let us say, solid friction, okay, where the frictional force is written as some coefficient of friction times the normal component of force. Then what do you do for the coefficient of friction? Usually it is given to you, is it not? How was it given to you? That means somebody has done experiments. This coefficient of friction will depend on the characteristics of the two mating surfaces. Is it copper on steel, or wood on aluminum, or is it aluminum aluminum? It depends on the combination, depends on the contact pressure, depends on the fluid filling the gap. If there is a liquid film, coefficient of friction will suddenly drastically diminish, which is the basis of using oil as a lubricant. It also depends on the surface texture, that means it depends on the extent of roughness of the two surfaces. So, it depends on hundreds of parameters, but still in your calculations you are given some coefficient of friction. So, that means people have studied coefficient of friction experimentally over a long period of time. They may also have theories on it. So, the subject of coefficient of friction has been separately studied, and from that database we just give you use mu equal to 0.1 or 0.4. Similarly, losses have been studied at great length in the literature, particularly because flow through a tube is a, let us say for a tube is a very, very important element. It is analogous to an electrical conductor. An electrical conductor carries current, while the tube carries flow. Okay. So, the tube becomes a very important part of our everyday life. So, this functions like this that I have written here, HF function of rho, mu, L, D and U has been studied in the literature theoretically as well as through experiments, and the data is available in handbooks. So, it is possible for a person, so it may require some experience to specify the losses. So, now you are depending on not your own experience, you are depending on the experience of the community, okay, the healthy aspect of it. And that experience is encapsulated in handbooks. But now handbooks also have a limitation, you can't specify it. Suppose I say I have a tube of 5 meters length and 10 mm diameter, show me the data. Then somebody else says I have 12 mm diameter, show me the data. It is not possible to generate data for each tube of each length, each diameter and each fluid. So, it is represented in compact form. So, handbook data will always be compact. Now, how do you compact a data set? That we will study maybe 3 lectures from now. Okay. So, a compact representation of experimental data. But an example of which has already been shared with you in the form of Moody's diagram, also called Moody's diagram or Moody's chart, where the term friction factor and Reynolds number, these are introduced. So, Moody's diagram is a plot of friction factor F as a function of Reynolds number for flow through a tube. So, this data is indicative of losses taking place in a tube. Is it a horizontal tube or a vertical tube? Any tube, inclined tube. Because losses do not depend on the orientation, though the pumping effort depends on orientation, but the losses do not depend on orientation. Okay, it is like saying the coefficient of friction between two mating surfaces will not depend on orientation. It is a local effect. Here, so this is handbook data. So, we have given you charts, but then all modern calculations, how are they carried out? On a computer through a program. So, if it is a program, you will say give me a formula. Okay, so, this data is available in tabular form, graphical form, or as algebraic expressions which you can evaluate. This Reynolds number R e is defined as rho u d over mu. Why this particular definition? That we will see later. This compaction of data is a topic to be studied. Rho is density, mu is viscosity, u is the fluid speed in the tube, d is diameter, inner diameter. In fluid flow, we are only interested in inner diameter. So, in a given problem, you can calculate Reynolds number straight away, for which you will need fluid properties. Okay. So, and this friction factor F So, in most problems your input will be Reynolds number and output would be losses, and the losses information is contained in friction factor. And this friction factor is defined as, this is one expression it is the change in pressure this delta P is pressure drop in a tube, horizontal tube, from where F is usually estimated. This is an original definition of friction factor. So, if you remember a horizontal tube, this is the governing equation for a horizontal tube. Which tells you that delta P over rho is well, actually this is P 2 minus, this delta P is P 2 minus P 1. Now, the friction factor is reported as a positive number. Okay. So, F is not negative. So, what you want is GHF. This is the quantity, if you remember the pump calculation, what you want is GHF. So, GHF is evaluated in terms of F as F L u square over 2D. Okay. I am just combining all those expressions. So, instead of giving you HF as 5 meters or 20 meters, losses are connected to velocity, length and diameter as well as fluid properties. In handbooks, one such important piece of information for tubes is in Moody's chart, find Reynolds number, find friction factor, from friction factor find the losses. GHF, G is acceleration due to gravity. So, if you divide by G, you will get HF, but in all those calculations, G and HF go together. Okay, so let me, okay, what is the shape of this graph? It's something like this. Okay, it's a logarithmic scale. So, the range of Reynolds number, we will discuss the importance of Reynolds number later, but Reynolds number depending on applications can go from 10 raised to minus 15, 10 raised to minus 15 to 10 raised to plus 20. The range is enormous, but the graph given to you I think is from 1 to 10 raised to 8 or something. It's much narrower range. The second interesting aspect of this graph is there is a break in the curve. Why is there a break? That we have to examine, but there is a break in the curve. And this graph is for a smooth tube. Okay, a tube, let us say a polished, you might have seen a smooth tube, polished tube, where there are no apparent roughnesses. If you think of let us say a concrete pipe, it is very rough. So, concrete pipe has roughness, steel tube will be practically smooth. So, as the tube becomes rough, this part of the graph shifts upwards, but nothing happens to the left side. The left side does not depend on, that means the initial part does not depend on the roughness. For higher Reynolds numbers, there is a dependence on roughness, and this jump occurs at about 2000. So, this is the shape of the graph. So, if you have to use Moody's diagram, you have to find Reynolds number, and then it turns out that in most real life problems you are on the right side of this graph. So, roughness has to be prescribed. If it is smooth, roughness is, how much is roughness for a smooth tube? 0. Okay. So, the lower limit is for 0 roughness, otherwise you have to pick the roughness and read friction factor out of it and then put it in the formula F L u square over 2D and find G H, and when you substitute there is a negative sign over there in the energy equation. Okay, so, this graph has been given to you. Let us see if I can show it. Here is, this is the graph. So, in the next at least 2 lectures, we will keep referring to this graph. If you have it in front of you, then you will be with me. So, whenever you say with me, then you have to have a statement which says without me. So, I am just trying to fill in the blanks, but I think I will leave it to your imagination. This is Moody's diagram sent to you, yes or no? See, since I don't hear from you, I think I can get a response by asking questions. This is an objective kind of questioning, yes or no? Is this right or wrong? It's objective kind of questioning. This is Moody's chart, yes or no? Yes, okay. You can see friction factor on the y-axis. Look at the numbers, 0.004, etc. These are all small numbers. And it starts with 100, I think. Reynolds number 100, though Reynolds number can be much smaller. On the smaller side, it's no big deal because it's a straight line, you can keep extrapolating. And epsilon is surface roughness. For a smooth tube, epsilon is 0. So, the lower line is for a smooth tube. And Reynolds number, okay, the definition given here is V bar is U, D is diameter over nu, that nu is mu over rho. Okay, we wrote rho u d over mu because we used rho and mu all the time, and that ratio mu over rho is the nu. Okay. This is the graph given to you. So, find Reynolds number, go to this graph and find friction factor, find losses, substitute in energy equation and evaluate pumping effort or turbine output, things like that. Okay. Answer the questions as required in the problem. So, we have 2 minutes, which is quite adequate for solving a problem. So, I have the numerical values here. By the way, the book always talks of 20 degrees Celsius, but let us agree we will talk of 30 degrees Celsius. Okay. So, if nothing is given, assume that the fluid is at 30 degrees Celsius and water density, let us say we are working with water, it is about 1000 mu is 79.77 10 raised to minus 6 units of Pascal second. Let us say, velocity is 5 meters per second. Let us say diameter is 50 mm. Naturally, you have to use consistent units. Okay, if it is kilopascal, you please convert to Pascal before evaluate. So, consistency of units is important. So, this will give you Reynolds number of 3.12 10 raised to 5 and will give you F equal to 0.0145. What are the units of Reynolds number? Show that Reynolds number is dimensionless. Show that friction factor is dimensionless. Okay, F L, that we had the definition of F. So, show that it is dimensionless. So, these quantities, and make sure that you get at least similar numbers. Reading that graph is not that easy, but try to get these numbers. So, and the next time we will do more numerical problems, okay, using Moody's diagram.